Hello friends, this video on isolation of elements part 1 is brought to you by examfear.com. No more fear from exam. The objective of this lesson is to explain the terms minerals, ores, concentration, benefaction, calcination, roasting, refining, etc. To understand the principle of oxidation, reduction. We'll also try to apply the thermodynamics concepts which we have learned in the principle of extraction. So we have learned all the thermodynamics concept. We have learned about the Gibbs energy, entropy. So we have learned this equation delta G is equal to nothing but delta H minus T delta S. So these all equations will apply in the extraction of metals. We will try to explain why the reduction of certain oxides, for example, this is easier than the reduction of other oxides. We'll also explain why CO, carbon monoxide, is a very good reducing agent at certain temperature, but coke is a good reducing agent at some other temperature. So that means we'll try to tell you the role of temperature also as far as reducing agent capability is concerned. We'll also explain why specific reducing agents are used for the reduction process. So for a given reduction process, you can use n number of reducing agents, but only some specific reducing agents are used. We'll explain why. So before we start the whole chapter, the first question that comes to our mind is, why should we study this chapter? Why should we study isolation of elements? So if you see things around us, the buildings, it has iron, steel. From where do we get this iron and steel? We talk about the wires that carry current is again a metal. From where do we get this? Who manufactures that? Who creates that? The big towers we see, it's all heavy metals. The bridges that we use, these bridges are made up of metals. Even the utensils we use is nothing but metal. It is stainless steel, right? The ships, the body of the ship is made of metal. The jewelry item is again a metal. The vehicle which we use, the engine, the body of these is again metal. The battery that is used has metal inside that, and we have studied this in the past few chapters. So from where do we get this metal? So actually, if you see, this is the metal we see in our day-to-day life, but actually you get these metals from ores. We'll talk about that ores in the next chapter, the next slide. So we get this pure form of metal. This is the one on the right hand side is pure metal, and we get this from the ores. So we use some chemical reaction, and we also use physical separation. We use n number of things here. There are n number of steps involved, and this is what we will try to learn in this chapter, because what we were interested in the pure metals, because these pure metals are used in these many things. In fact, there are more applications. We talk about the building, battery, wires, stainless steel utensils, cars, jewelry, bridges, ships. A lot of places we use metal, but actually you don't get pure metal in the earth. In the nature you get these ores, right? So from these ores we do follow some process, we have some steps, and we extract pure metal from these ores. And these ores are nothing but when you dig this earth crust, you'll get something. You'll get these ores. Not all the places, some places, that's why you'll see that gold is fine in some places, in some gold mines. Iron is fine in some places of the country. So these are ores, and these ores come from the earth crust, and these can't be used directly because they are not the pure form. It has to be purified so that we can use them, right? So there are some steps to purify that, and we'll try to learn the steps, because see, so much production of metal is required, correct? Because the metals are used in so many places. So we have to optimize this process. This process to create pure metal from the ores, we have to optimize it so that we can get more and more better quality of pure metal. right? And here we'll see that to optimize this process, we can use the principle of thermodynamics, right? Because thermodynamics will help us to choose the best reducing agent. For example, normally ores are in the form of oxide. So for example, I have oxide ore FeO, and then I have to make it iron. Then I'll use reducing agent like carbon. It will give me iron and carbon monoxide. This is my metal. This will be almost pure. Then we can make it ultra pure. So here, since if you see oxidation and reduction both are happening, so here thermodynamics will help us to choose this reducing agent. Which one is the best reducing agent at a given temperature? Thermodynamics will help me to choose, right? It will also help us to find a minimum temperature required, because here some temperature will be required. Minimum temperature required for this reaction to happen, because we have to follow this process in a large scale. Why? Because this pure metal is required in the large scale. Anything if you do in bulk, in large scale, it is good to have the process optimized. So in this chapter, I will try to understand the whole process and try to see how can we optimize this. How can we get the best reducing agent? How can we get the best temperature? Right? So, and that's the reason why we are studying this chapter, because if you see, most of the metals we get in the earth crust is in the combined state. Only few of them are in the free state. For example, gold is in free state generally. This is not gold, as in this is a copper. So gold is in free state, and carbon, sulfur, they are other elements which are in free state. But typically most of the elements which we get in the earth crust, from the earth crust, are normally in the form of oxides or sulfides or carbonates, right? For example, ferrous oxide, ferric oxide, so they're generally in this form, right? So we have to somehow purify them, correct? So hope you understood the logic. So there's a huge demand of pure metal, and all this pure metal come from the ores, from the earth crust. So we have to optimize this process of creating the pure metal from this, right? So this is all about metallurgy. So the whole process of metallurgy and the isolation should be such that, first thing is it should be chemically feasible, and the second thing is it should be commercially viable. I have introduced this term minerals and ores. Let's understand the difference between minerals and ores. Mineral, the term came from mine. Mines, you know, the coal mines, from where you get the coal. So from the earth crust, you dig and you get something that is called mineral. But not all minerals are ore. Correct? See, for example, you want to get this metal. This is some metal. Let's suppose this is zinc. And this zinc actually you can obtain chemically from this ore 1, ore 2, these are all ores, ore 3 or ore 4. All these ores will actually give you zinc. Or all these minerals, they are all minerals, I'll say. They are all minerals. Mineral 1, mineral 2, mineral 3, mineral 4. All these minerals will actually give you zinc. But out of these, only few will be used. Why? Because maybe to produce, let's suppose 1 kg zinc, and 1 kg zinc cost is, let's suppose, X dollars or X rupees. Let's assume $100, right? If you use mineral 1, the total cost involved is $50. If you use mineral 2, the total cost involved is $80, let's suppose. If you use mineral 3, the total cost involved is $120 to prepare 1 kg. If you use mineral 4, the total cost involved is $150 per kg. Right? So in this case, if you see, the dollar also comes into picture. So in this case, if preparing 1 kg zinc needs $150, but the cost of zinc is $100 only, so this mineral will not be used. Similarly, this mineral will not be used. But these two minerals are useful, and this is more useful because only $50 is required to prepare this 1 kg of zinc, and the total cost of zinc is $100. So what I'm talking about is the minerals from which you can extract the metals economically. It should be economically viable. Only those minerals are ores. So ores, when you talk about the ores, the economy also come into picture. Correct? And also when you talk about the minerals and ores, I'll also introduce a new term called gangue. Gangue. So these are nothing but unwanted particles in this ore. Stones, mud, those kind of stuff. Or for example, if you talk about ore for zinc, if it has iron also in this trace amount, then iron becomes gangue for this. Correct? So gangue is nothing but unwanted particle. So that's all about minerals, ores and gangue. So mineral is nothing but something which occurs naturally. But out of this is mineral is nothing but anything which occurs naturally in the earth crust is my mineral. Ores is minerals from which you can extract metal economically. Out of these 4 minerals, only 2 were ores. Correct? And all these ores will contain unwanted particle, and that will be called gangue. Right? So what is metallurgy? As I told, metallurgy is nothing but scientific and technological process of isolation of metal from its ore. So this is my ore. When you talk about ore, you talk about the money part, whether it is economically feasible. From this ore, you get metal, and that's why it's called metallurgy. Correct? So to do this, from ore to metal, we need what? We need scientific and technological process. Because this technology evolves, we keep on generating new and new better process. And it has to be scientific. So this process to get metal from ore is called metallurgy. Correct? Now I told that metal exists, or the ores of this metal occur in the earth crust, right? So if we talk about the abundance, aluminum is the most abundant metal in this earth crust. The first is aluminum. It is the most abundant metal. Talk about the metal. And actually, if you talk about the element, then this aluminum has the 3rd position. If we talk about the element, because there are other elements. Element is a superset of metal. We know that element can be metal, non-metal, metalloid. So, but if we talk about the metal, this is the most abundant, aluminum. 3rd element in the earth crust and first metal. Correct. So it is generally found in igneous mineral, micanthal. This is a typical ore for aluminum. And also, if you see in the gemstones, also aluminum exists. This is Al2O3 in the form of gemstone. If you see, this is ruby and sapphire. So in ruby you have chromium as impurity, and in sapphire you have cobalt as impurity. Correct. If we talk about the ore of aluminum, you have bauxite. Bauxite is the ore of aluminum. The next metal I'll talk about is iron. That is again the second most abundant metal in the earth crust. Correct? So here for iron, mostly oxides are used as the ores. Aluminium also, it exists in the forms of oxides because they are little reactive metals and they don't exist freely. So if we talk about some of the important metals, this is the chart. Aluminium, if you see, the most important ore is bauxite. And this is the formula AlO some x and OH to the power 3 minus 2x. Not to the power 3 minus 2x in the superscript. Similarly, for iron, these are the ores: hematite, magnetite, siderite, iron pyrite. Right? So if we talk about the hematite, in fact, this is also for aluminium. If we talk about hematite, the formula is Fe2O3, magnetite Fe3O4, siderite FeCO3, this is a carbonate ore, and FeS2 is again sulfide ore. So if you see, iron exists in oxide, carbonates, and sulfide. That's all about iron. If we talk about the copper, copper exists in sulfide, carbonate, oxide, again sulfide. So these are the 4 ores, popular ore for copper: copper pyrite, malachite, cuprite, and copper glass. If we talk about zinc, zinc has these 3 popular ores: ZnS, also called zinc blende, calamine, ZnCO3, and zincite, ZnO. So if you see, sulfide, carbonate, oxide, all 3 ores are there. So typically we have, as I told, carbonates or oxides or sulfide. Why? Because if you see, carbon exists in nature, oxygen exists in nature, and sulfur exists in nature. These metals only combine with carbon, oxygen, and sulfur to form carbonates, oxides, and sulfides. And that's why you get these ores in carbonates, sulfides, and oxides form. Correct? So for aluminium, please remember this chart. For aluminium, the best ore is bauxite, and iron, hematite, magnetite, siderite, iron pyrite. Copper, generally we use copper pyrite, and zinc we use zinc blende. Now please note that before we proceed further, these ores, when you get this from the earth, it has huge amount of impurities or huge amount of gangue, mud, sand, rocks. So these has to be removed. That is the first process, so that we get the reasonable amount of impurities. So once we get the reasonable amount of impurities, then we start our chemical process. So before we start the chemical process on all these ores, first we try to remove the impurity like sand, mud. So we have different process for that. We'll talk about that. And we generally call that concentration of ore. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.